Hi everyone, let's see how we can change the order of integration in a double integral with some examples. Suppose we want to evaluate this integral, this double integral. Here we have the domain of integration. We're going to talk about it more later. Let's try to integrate this. Well, first we have to integrate with respect to x. So the integral with respect to x here, y is a constant when we integrate with respect to x, so we regard y as a constant, and the integral of something, some constant over x plus 1 is just its natural logarithm. So we get the integral from 0 to 1. Well, 2y is a constant when we integrate with respect to x, and the integral of 1 over x plus 1 is ln of x plus 1. And of course we are integrating from x equals 0 to x equals y. And then we have to integrate the resulting function with respect to y. So at x equals 0 we get ln of 1, which is 0, so we are left with 2y ln of y plus 1 dy. So we have to, at the end, we have to evaluate this one-dimensional integral, this ordinary integral. Now, it's possible to integrate a function of this type. You have to integrate it by parts. You can see my video on integration by parts. But there is another way here that we can try, and it's a very important technique in practice. We can change the order of integration here. Here we're first integrated with respect to x and then with respect to y. We can switch the order of integration and try integrating with respect to y and then with respect to x. Sometimes this makes the problem much more simple. Now, when you switch the integrals, when you change the order of integration, well, the function doesn't change, and the domain of integration doesn't change either. So here is the domain of integration in this example. The domain of integration doesn't change either, but the way that we traverse this domain will change. So these parameters here will change. So let's look at this integral more closely. So here y is a constant in this inner integral. So for a constant y, so y is a constant here, for a constant y, x changes from 0 to this point, which is y. This line is y equals x. So for a constant y, x changes from 0 to y. And then y goes from 0 to 1, and for any y, x goes from 0 to y. So that's what we have here. But if we change the order of integration, then x goes from 0 to 1, but for any fixed x, y changes from this point, which is x, to this point, which is 1. So for any fixed x, y changes from x to 1. So when we change the order of integrals, we get the integral, well, the function doesn't change. Remember, this time we first want to integrate with respect to y and then with respect to x. Now, x changes from 0 to 1, and for any fixed x, y changes from x to 1. Now let's try to evaluate this integral. We get integral from 0 to 1. The integral here, when we integrate with respect to y, x is a constant. So we are essentially integrating to y, whose integral is just y squared, and the constant x plus 1 remains there. And of course y goes from x to 1. And then we integrate with respect to x. Now we have the integral from 0 to 1. Y squared at 1 is 1, minus y squared at x, which is x squared, over x plus 1 dx. But 1 minus x squared is 1 minus x times 1 plus x. So we can simplify here, we get 1 minus x. So we are left with a much simpler integral than before. We get the integral from 0 to 1 of 1 minus x dx, which is x minus x squared over 2 from 0 to 1, which is 1 minus half its half. So as you see, changing the order of integration resulted in a much simpler integral. Before we had to use integration by parts to evaluate this, but now we just simply integrated a linear function. And this happens in some examples, but even without that, being able to correctly change the order of integration is itself a very important concept and technique. Let's see another example and practice more. Suppose we want to integrate this function 2x y squared over this region. Now again, we have this region here. So it says that the integrals say that as x changes between 0 and 4. So x changes between 0 and 4. And for any fixed x, y changes from this minus the square root of 4 minus x to plus that. So for any fixed x, y goes from minus the square root of 4 minus x to plus the square root of 4 minus x. And this determines a parabola with this equation, x equals 4 minus y squared. Now again, when we change the order of integration, the function doesn't change. The domain of integration doesn't change either, but the way that we see it in these integrals, the way that we traverse the domain, it changes. So let's rewrite this. So this time, well, y, we can say that y changes from minus 2 to 2, and for any fixed y, so y goes from minus 2 to 2, and for any fixed y, x changes from 0 to the point on the parabola, which is 4 minus y squared. So we get the integral from 0 to 4 minus y squared. The function doesn't change. dx dy. Now let's see where these integrals lead us. So the first integral, if we try to integrate the first integral, we get, well, the integral of 2xy squared with respect to y is 2x y cubed over 3, and we are integrating from minus the square root of 4 minus x to plus that. You can of course plug these into y cubed. You get 4 minus x to the power half to the power 3. So 4 minus x to the 3 halves times x minus some similar term. It is possible to integrate that, but it is a very messy integral. It's very complicated. But if we change the order of integration, we get a much simpler integral. So now if we integrate here first with respect to x, we get the integral of 2x y squared with respect to x is, y squared is a constant here, so we get y squared, the integral of 2x is x squared, from 0 to 4 minus y squared dy. We get the integral from minus 2 to 2, x squared at 0 is 0, x squared at 4 minus y squared is, well, we have a y squared times 4 minus y squared squared dy. Now we just expand this and integrate it. It's a simple polynomial. We get the integral from minus 2 to 2 y squared times 4 squared, which is 16, minus 2 times 4, 8y squared plus y to the 4th dy, which is the integral from minus 2 to 2, 16y squared minus 8y to the 4th plus y to the 6th dy gives us 16y cubed over 3 minus 8y to the 5 over 5 plus y to the 7 over 7 from -2 to 2. And as you see, this was a much simpler integral than the previous one, and you can just plug these values in and evaluate the exact value. That's a very simple thing. You can do it with a calculator, but the integral itself is much simpler than the previous one. So changing the order of integration here again resulted in a much simpler integral.